physics and chemistry, laureate in economic sciences, Your Excellence, members of the Academy, ladies and gentlemen. Those who have the ability to observe what nobody else is able to see, enlighten the world, and bring knowledge to the benefit of mankind. As expressed by Arthur Schopenhauer, talent hits a target no one else can hit. Genius hits a target no one else can see. The role of science is to question what is regarded as the truth, to uncover hidden phenomena, to see the possibilities which are obscure to the narrow mind, as in René Magritte's La Clairvoyance, to think outside the box, as we would say today. The passionate observer, equipped with imagination and creativity, leads us forward to a better world. This requires hard work and occasionally courage, since it happens that those who pave the way are met by distrust or even resistance. Today, the Church does not ban the scientists like they once did with Galileo, but the world is not even prepared to accept scientific achievements, and even the scientific community may need time to recognize and accept. But at least slowly, new paradigms are accepted, as suddenly a new interpretation of an image appears. Then it is not possible to unsee. To understand the world we live in, we need to understand the nature of the invisible building blocks that matter is made up of. The tiny neutrino has captured the fascination of not only the scientist, but even of a writer like John Updike, who made poetry of the particle assumed to have no mass. It reads, "Neutrinos, they are very small, they have no charge and have no mass, and do not interact at all. The Earth is just a silly ball to them, through which they simply pass, like dust mites down a drafty hall or photons through a sheet of glass." Now the poem has been ruined because we know that they have a tiny mass, but instead we have gained a more profound knowledge of the world we live in. Our DNA, although giant creatures compared to the pretty neutrino, are traveling tirelessly from generation to generation, seemingly resistant to all attacks, until the naked eye uncovered their nature, detected their fragility, but also their ability to heal. We live in a dark world with terrorism, refugees, and where many people still live in poverty. But new insight and unconventional ideas help to find ways to improve the living conditions and promote welfare for those who are exposed to poverty. We need to trust in science, because only knowledge can make the world better. Alfred Nobel recognized the importance of science and those who uncover what has been hidden, who explain our mere existence, who improve the quality of our lives, who open doors for future findings. This week is the big celebration of science, and today we are going to listen to some of those who have increased our knowledge and made a difference to the way we think. I will now ask Professor Lully to introduce the Nobel Prize in Physics.
Dear laureates, ladies and gentlemen, it's a pleasure for me to introduce the Nobel Prize in Physics. We are talking about neutrinos. Neutrinos have very interesting and fascinating properties. They are very abundant. They are almost as abundant as photons. There are many billions of neutrinos in this room at this moment. They travel almost at the speed of light. Neutrinos are very elusive particles. They interact via the weak interaction with a very short range. That means that they travel in this room and they are not affected. They travel through Earth without being absorbed or anything. They just go through. Neutrinos have three flavors. They can be electron, muon, or tau. And they can change flavor, and this is this year's Nobel Prize discovery. They oscillate. We are talking about neutrino oscillation. Neutrinos have a mass, and this is because of this year's prize discovery. They were assumed to be without mass. Now we know that they have a mass. Very small mass, but since there are so many of them, this is a large mass. And this is changing our understanding of the universe. The discovery was made in two scientific collaborations, one in Japan, with as prominent scientist, Professor Takaaki Kajita. It's called SuperKamiokande. They were looking at neutrinos, atmospheric neutrinos created when cosmic radiation interacts with the molecules of the atmosphere. The second collaboration is in Canada, Sudbury Neutrino Observatory collaboration led by Professor Arthur B McDonald. It's now time for me to introduce the first Nobel laureate, Professor Takaaki Kajita. He was born in March 1959 at Higashi-Matsuyama, Japan. He studied first at Saitama University and then at the university in Tokyo, where he got his PhD in 1986. And since 1988, he has been at the Institute for Cosmic Radiation Research. In 1999, he became professor at the University of Tokyo and is director of the Institute for Cosmic Ray Research. So, Professor Kajita, please.
Good morning. Well, first of all, I'd like to thank the very kind introduction. And also, I want to mention that this is really the greatest honor for me to give this lecture today. Today, I'm going to discuss discovery of atmospheric neutrinos. Well, the outline of this talk is shown here. First, I have an introduction. That is the introduction of the Kamiokande experiment. That was the starting point of my research. Then I want to discuss the atmospheric neutrino deficit. And then the discovery of neutrino oscillations, recent results, and the future. Then I'll summarize, and finally, I want to mention the acknowledgement. Now, introduction. Well, in the late 1970s, new theories that unify strong, weak, and electromagnetic forces were proposed. These theories predicted that protons and neutrons, namely nucleons, should decay with the lifetime of approximately 10 to 28 to 10 to 20, 39 years, 32, sorry. This is long enough to think about the real effect. However, these are short enough to observe the proton decays. Therefore, several proton decay experiments began in early 1980s, and one of them was the Kamiokande experiment. No lasers. Well, okay. This is the photo of the Kamiokande experiment. It is a 3-kiloton water Cherenkov detector, and the fiducial mass for the analysis of neutrino events or proton decays was about 1 kilotons. And I'd like to tell you the basics of this experiment. Yeah. Well, if a relativistic charged particle propagate in water, then they emit Cherenkov light. And these photons, Cherenkov lights, are detected by photon detectors that are placed on the wall of the detector. And you can see these dots are actually photodetectors. And I want to mention that initially, Kamiokande was rather a small experiment. Well, this was the, I would say, construction team in spring of 1983. And you can see here is Professor Koshiba, who is the Nobel laureate in physics in year 2002. And also you can see Professor Totsuka, Professor Kifune, and also you can see students maybe 2-3 meters behind Professor Koshiba. And one of them was me. Well, okay. There was already an introduction of neutrinos. Therefore, for this page, I could be short, but let me repeat. Neutrinos are fundamental particles like electrons and quarks. They have no electric charge, and they have 3 types or 3 flavors: electron neutrinos, muon neutrinos, and tau neutrinos. And they are produced in various places, such as the Earth's atmosphere or center of the sun. And they can easily penetrate through the Earth, or maybe even the sun. So if a neutrino is produced here, they can easily propagate through the Earth, unfortunately also through the detector, and go to the space. But, well, they can, however, interact with matter very rarely. If interaction occurs, nu mu produces a muon, and nu e produces an electron. And also, I want to mention that in the very successful standard model of particle physics, neutrinos are assumed to have no mass. However, physicists have been asking, neutrinos really have no mass. Now, I want to move on to the atmospheric neutrino deficit. Well, I want to explain a little bit. Cosmic ray particles entering in the atmosphere interact with the air nucleus. Then these interactions typically produce pions, and then these pions decay to muons, to electrons, and in this decay chain, 2 muon neutrinos and 1 electron neutrinos are produced. And these are observed in underground detectors. Now, I want to mention a little bit my work in early days. I got my PhD in March 1986 based on the search for proton decay. Well, of course, I didn't find any proton decay. But anyway, I felt that the analysis software was not good enough to select the signal that is proton decays from the background, that is the atmospheric neutrino interactions, most efficiently. Therefore, as soon as I submitted my thesis, I began to work to improve the software. And one of them was the analysis software to identify the particle type for multi-Cherenkov ring events. Namely, I wanted to know if, say, each Cherenkov ring in a multi-ring event is produced by an electron or muon. For example, this is an observed event in Kamiokande. And you can see 3 Cherenkov rings here, and I wanted to know if they are produced by a muon or an electron. Anyway, the new software was ready and was applied to single Cherenkov ring events, which were the easiest events to analyze. So it's natural to start from the easiest thing. Then, the neutrino flavor was studied for the atmospheric neutrino events. These are the typical events observed in Kamiokande. This is a typical event pattern for electron-neutrino interaction. This is the typical event pattern for muon-neutrino interaction. And we immediately found that the result was strange. The number of muon-neutrino events was much fewer than expected. Well, at first, I thought that I made some serious mistake. In order to know where I made mistake, I decided to scan the events. And immediately, I realized that the analysis software was right. However, I was not optimistic yet. I thought that it's very likely that there were some mistakes somewhere in the simulation, data reduction, or event reconstruction. So that means mostly Takita-san and myself, started various studies to find mistakes in the late 1986. Well, actually, after more than 1 year of studies, we concluded that mu deficit cannot be due to any major problem in the data analysis nor the simulation. And therefore, Kamiokande decided to publish this result. And well, basically, in this paper, in this publication, we reported these numbers. The number of electron-neutrino events observed was 93, while the predicted number was 88.5. So basically, they agree. However, for the muon-neutrino events, the number of observed events in the data was 85, while the prediction was 144. It's clear that there is a deficit in the new mu events. And in the paper, we concluded that we are unable to explain the data as the result of systematic detector effects or uncertainties in the atmospheric neutrino fluxes. Some as yet unaccounted for physics, such as neutrino oscillations, might explain the data. Well, at this stage, this is still might. However, well, I got very much excited. And well, I want to mention my personal memory. Well, I was mostly excited with the possibility of neutrino oscillations with large mixing angle. Namely, nu mu seems to oscillate maximally to the other neutrino type, and this maximal oscillation was not expected. Therefore, I got excited, and this gave me the strong motivation to continue the study. Now, I mentioned neutrino oscillations, so I want to explain a little bit about neutrino oscillations. This was also mentioned already at the beginning, therefore I would not be very precise. But anyway, if neutrinos have masses, neutrinos change their flavor or type from one flavor to the other. For example, oscillations could occur between mu neutrinos and tau neutrinos. And if a mu neutrino is produced here, then if they propagate long distances, they disappear, and if they propagate even further, they reappear. And if propagate further, disappear again, reappear again. And if mu neutrinos disappear, then tau neutrinos appear. So this is the neutrino oscillation. And one important thing is, if the neutrino mass is smaller, the oscillation length, that is, well, for this figure, maybe this distance gets longer. So in order to study small neutrino masses, you have to study neutrinos that traverse long distances. And also, I want to mention that these are theoretically predicted by these people, Maki, Nakagawa, Sakata, and Pontecorvo. Now, so far, I have discussed the Kamiokande result, but, well, there was other experiment called IMB. That was another large water Cherenkov detector, and they also reported the deficit of muon neutrino events. So that is encouraging. However, well, we thought that the simple deficit of muon neutrino events is not really enough to conclude to be neutrino oscillations. We wanted to have more positive evidence for oscillations. Then, well, actually the physics is simple. If neutrinos are produced in the upper atmosphere of a detector, then the travel lengths for neutrinos are short enough. Therefore, they have no time to oscillate. However, if a neutrino is produced in the other side of the Earth, then they need to travel long distances before reaching to the detector. So they may oscillate. Therefore, we conclude that we should observe the deficit of upward-going muon neutrinos. And in fact, Kamiokande tried to see this effect. And well, we studied, but we see some effect. However, it was clear that Kamiokande was not big enough to be conclusive. Therefore, it's clear that we needed much larger detector, and therefore we needed SuperKamiokande. Now, I want to move on to the neutrino oscillation discovery. Well, of course, the discovery was made by the SuperKamiokande experiment. It is a 50 kiloton water Cherenkov detector, and the fiducial mass that is used for the oscillation studies is 22.5 kilotons, which is more than 20 times larger than the fiducial mass of Kamiokande. And this is a big experiment and big international collaboration we have about 120 collaborators from these countries. I said this is an international collaboration, and in fact, this is an international collaboration from the beginning of the construction. And this photo shows the initial discussion about the SuperKamiokande collaboration between Japan and the United States. And here you can see Professor Tosca, who was the spokesperson of the SuperKamiokande. And also you can see various key people in this photo. And this photo was taken at the Institute for Cosmic Ray Research, probably in 1991 or 1992. Now, this is the photo of the SuperKamiokande detector. Well, this was taken in January 1996, and you can see the pure water was filled up to this level, and you can realize how big the detector is if you notice 3 people on a rubber boat. Anyway, the SuperKamiokande detector was constructed and started the data taking in April 1996. And since then, SuperKamiokande has been observing lot of atmospheric neutrino events. This is the typical single Cherenkov ring event observed in SuperKamiokande. In addition, we have these events, and you can clearly see 2 Cherenkov rings in the event. Furthermore, we have this kind of event. This is the neutrino interaction occurring in the detector, but the charged particle, in this case muon, penetrates through the inner detector, and you can in fact see the signal in the outer detector. In addition, we have yet another sample, that is the upward going muons. Here, the neutrino interact in the rock below the detector, and only a muon is observed. Here, you can see a muon enter from this point and exited at this point. So these muons come from below and penetrate to the top. And I want to mention that all these events are used in the analysis, and each event have a very different event topology. Therefore, we need to work coherently, and collaborative work of many people, or more exactly, many young people, were essential to the discovery. Anyway, after 2 years from the beginning of the SuperKamiokande experiment, we conclude that the data gave the evidence for neutrino oscillations. And this is the slide used in neutrino conference in 1998. And this is the most important plot in that presentation. Well, let me explain a little bit. Well, this is the zenith angle distribution, and cosine theta equal 1 means neutrinos coming from above. Cosine theta equal -1 means neutrinos are coming from below. And you see that for neutrinos coming from above, the observed data, which are shown by the black dot, are in agreement with the prediction, which is shown by these squares. However, if we look at the neutrinos coming from the other side of the Earth, we clearly see the deficit. And from this result, together with the other data, SuperKamiokande concluded that the observed zenith angle dependent deficit, this one, and the other supporting data gave evidence for neutrino oscillations. Well, so far I discussed the result from SuperKamiokande. At that time, there were other atmospheric neutrino experiments. They are Macro in Italy and Sudan 2 in the United States. These experiments observed atmospheric neutrinos and confirmed neutrino oscillations. Therefore, the neutrino oscillation was quickly accepted by the neutrino community. Now, in the remaining time, I want to discuss a little bit about the results, recent results and the future. Well, I said, essentially based on this distribution, we concluded that neutrinos oscillate. Well, it was very nice to say that approximately half of the long-traveling muon neutrinos disappear. However, we think that we want to really confirm neutrino oscillations. And if we look at the prediction, so oscillation probability as a function of log of distance should be like this. So we really wanted to observe this dip in order to confirm really neutrinos oscillate. And therefore, SuperKamiokande carried out a special analysis, and in fact, observed the deep. Well, the deep is not as deep as this deep, but anyway, this is the data. The depth of the deep is just consistent with the prediction if we consider the detector resolution. So we are very happy that the deep was seen at this position, and this really tells us that neutrinos really oscillate. Well, we discussed the neutrino oscillation discovery in 1998. SuperKamiokande is still taking data. And I would like to compare the neutrino data in 1998 and the data so far accumulated. At Neutrino conference in 1998, we used 531 events in order to produce this plot. And if we do the same now, then the number of events used in this plot is 5,485. So we have 10 times larger data sample, and we are continuing detailed studies of neutrino oscillations. And here, at this point, I want to mention two main results. Well, first of all, heaviest neutrino mass is approximately 10 million times smaller than the electron mass, which is actually the lightest particle except for neutrinos. So you can realize that neutrinos mass is really, really, really tiny. In addition, we found that mu oscillate maximally to nu taus, which is, to me, really surprising, and we really want to understand why. Now, I want to mention a little bit about the overall history or development of neutrino oscillation experiments. As I said, the early mu deficit was concluded to be neutrino oscillations, and this discovery motivated the accelerator-based neutrino oscillation experiments to further study oscillation effect. And these studies, together with the updated atmospheric neutrino data, requires the full three-flavor oscillation effects. And well, this effect biggest effect was already observed by these experiments. However, the story is not complete yet. The neutrino community is trying to understand further which could be the most important parameter to be observed. So I would say that our understanding on neutrino oscillations have been improving tremendously. However, we still have to understand neutrinos more. Now, I will summarize. Unexpected mu-neutrino deficit in the atmospheric neutrino flux was observed in Kamiokande in 1988. Subsequently, after 10 years, in 1998, SuperKamiokande discovered neutrino oscillations, which shows that neutrinos have mass. I feel that I have been extremely lucky because I have been involved in the excitement of this discovery from the beginning. The discovery of non-zero neutrino masses opened a window to study physics beyond the standard model of elementary particle physics, probably that of the grand unification of elementary particle interactions. There are still many things to be observed in neutrinos, and further studies of neutrinos might give us fundamental information for the understanding of the nature, such as the origin of the matter in the universe. Well, before concluding, I would like to acknowledge people who contributed to the discovery. First of all, I want to thank collaborators of Kamiokande and SuperKamiokande experiments. In particular, I would like to thank Masatoshi Koshiba and Yoji Totsuka for their continuing support of and encouragement of my research throughout my career. Ed Carnes worked with me on the analysis of atmospheric neutrinos in SuperKamiokande for many years. Masato Takita and Kenji Kaneyuki worked with me in the Kamiokande analysis. Yoji Totsuka, Yoichiro Suzuki, and Masayuki Nakahata have been leading the SuperKamiokande experiment. Hank Sobel and Jim Stone have been leading the US effort of SuperKamiokande. Kenzo Nakamura and Atsuto Suzuki played very important roles in the early stage of the SuperKamiokande experiment. And last, and maybe the most important, hard work by young collaborators of SuperKamiokande was essential for the discovery. And I also want to thank Morihiro Honda for the neutrino flux calculation, and finally, SuperKamiokande acknowledges MEXT, DOE, and Kamioka Mining and Smelting Company. Well, thank you very much for your attention.
We thank Professor Kajita for a very nice lecture. And now we turn to neutrinos from the sun, and it's a pleasure for me to introduce Professor Arthur McDonald. He was born in Sydney, Nova Scotia, Canada in 1943. He studied at Dalhousie University in Nova Scotia, and then at the California Institute of Technology in the US, where he became a doctor in 1969. He worked at the Chalk River Nuclear Laboratories until 1982, and then he became professor, first at Princeton University, and then later at Queen's University, Kingston, Canada. And is presently director of the Sudbury Neutrino Observatory Scientific Collaboration. So please, Professor McDonald.
Thank you. This is a great honor for me and my colleagues to, and we would like to thank the Royal Swedish Academy of Sciences and the Nobel Foundation for this tremendous honor. It's also an honor to share this prize with Professor Kajita and the members of the SuperKamiokande collaboration for the beautiful work that you just saw. So I'm going to tell a slightly different story, a story that was happening in parallel with the one you just heard, and one which was attempting to address neutrinos that come from the sun, a case where it had been a possibility that the explanation for what had come to be known as the solar neutrino problem was due to flavor change for neutrinos, in this case electron neutrinos produced in the core of the sun. And so I'm going to tell you about how that was done with the Sudbury Neutrino Observatory, which is actually represented in reality here. This is a picture taken looking up from the bottom of the sphere surrounded by light sensors in much the same way that light sensors were used in the SuperKamiokande experiment. So neutrinos, you've heard about their properties. They can penetrate through almost anything. They're a wonderful way to study what's happening directly in the core of the sun. 8 minutes ago, they travel almost at the speed of light. They're produced prolifically by the fusion reactions that are powering the sun. And they reach us here on Earth, and they can even penetrate through to our detectors, which in our case were situated 2 kilometers underground. The story of the sun is a long one, and this phrase that we stand on the shoulders of giants is something that is very true in this case. Hans Bethe and William Fowler, who was the head of the laboratory in which I studied at Caltech in 1969, have developed the understanding of how the nuclear reactions power the sun. And Ray Davis and John Bacall were pioneers in the study of neutrinos from the sun. Ray Davis with his chlorine-based detector, who observed that the number of neutrinos that he measured were about 3 times smaller than what was calculated by very sophisticated calculations that John Bacall and collaborators carried out. Bruno Pontecorvo was mentioned earlier, and along with the Japanese collaborators who put forward what we these days refer to as the MNSP approach to understanding the 3-flavor oscillations. At the time that the deficit was observed by Ray Davis, Pontecorvo and Gribov suggested that perhaps the explanation for why too few neutrinos were being observed was that electron neutrinos had been changing into muon neutrinos in transit from the core of the sun. At that point, of course, the knowledge of 3 neutrino types was not present, and that was expanded later to the thought that it was the possibility of oscillation into either of the other 2 types. The actual reactions that are occurring in the sun that produce the neutrinos, you can see the neutrinos circled in red here, are as shown here. This is what the energy release in the processes shown here are what produces the power in the sun. In 1984, the start of the SNO collaboration occurred because Herb Chen asked whether it's conceivable to obtain enough heavy water from Canada's reserves to perhaps do an experiment in Canada using that heavy water. There was a wonderful correspondence with George Ewan, who's here with us today, who had been looking for the opportunity to do underground science in Canada and had identified an ideal location, which was provided to us by the International Nickel Company in Sudbury, Ontario, a very deep location. And the idea that Herb put forward was that if you studied these are the highest or close to the highest energy neutrinos produced, if you had enough heavy water, you could conceivably make a measurement in which you could not only observe the type of neutrinos that were being produced in the core of the sun, but also observe the sum of all other neutrino types. And so a direct comparison of those two things would tell you whether the electron neutrinos were changing into the other types without recourse to calculations of how many were being produced in the core of the sun. And so in 1984, a collaboration came together. This shows a collaboration picture at Chalk River in 1986, and it also at the bottom shows a paper that was published at that time, putting the concept forward. The spokespersons at that point were Herb Chen for the United States, George Ewan for Canada. They were joined about a year later when the UK joined the experiment as led by Dave Sinclair. And we started attempting to develop this experiment. Unfortunately, about 6 months after this picture was taken, Herb Chen passed away from leukemia, much too early in age. And we still miss him and regard him as a substantial origin of this experimental collaboration. After Herb passed away, I took over as the US spokesperson for the project, and in 1989 became the director of the project, as we were all working very hard to put together this experiment. In the meantime, we had been joined by more groups in the United States and Britain, and we had a more substantial collaboration at the time that we were funded in 1990. So how did we detect neutrinos from the sun? Well, those billions that are streaming out from the sun require a large amount of material in order to obtain enough interactions to get statistical accuracy on the numbers that are, in fact, being observed, both in the category of electron neutrinos and other types. And so we needed a big detector. And we also needed the properties of this rather unique material, heavy water. About 1 in 6,400 molecules of ordinary water that you drink have an extra neutron in the nucleus, in the hydrogen nucleus, making it deuterium or D2O rather than H2O. And we were able to borrow 1,000 tons of this material, and that's what we used as the basis for our detector. If you have that material, then there are some specific reactions that you can observe, in all cases using the same Cherenkov radiation as was described to you earlier for the SuperKamiokande experiment, and using light sensors surrounding this tank of heavy water. The first one is very specific to electron neutrinos. We call it the charged current reaction, and I will refer to CC later on as a mnemonic for this particular reaction sensitive only to electron neutrinos. In this case, a deuterium, of course, has a neutron and a proton in it. As you can see here, one of those neutrons is changed into a proton and a fast-moving electron that produces Cherenkov light in your detector. The second reaction, which is a unique one for deuterium, is one in which any neutrino type with equal sensitivity, electron, mu, or tau, can break deuterium apart, giving you a free neutron. We used 3 different techniques to detect those neutrons in different phases of the project. And that particular case is only sensitive to, well, it is sensitive to all neutrino types. And so if you compare these two, then you're able to tell if the number of electron neutrinos is the same as the total, in which case nothing will have happened. But as we eventually observed, we only saw 1/3 as many electron neutrinos as the total, demonstrating that neutrinos had changed their type. You have to be very careful when you're trying to do this measurement, because it is possible for radioactivity, particularly gamma rays, to break deuterium apart, producing a free neutron. And so we had to control radioactivity extremely carefully in order to be sure that we were not seeing a false signal from that radioactivity, and therefore we went to great lengths to control radioactivity in our experiment. There is another reaction in which the neutrinos strike electrons, and this is in fact something that SuperKamiokande also used to look at solar neutrinos. It has predominantly a sensitivity to electron neutrinos, but it has a small sensitivity also to all neutrino types. And in fact, before our full result using the first two reactions, we combined our data with data from SuperKamiokande and had a preliminary indication that neutrinos from the sun were in fact oscillating. The three techniques we used for detecting the neutrons are a little complicated technically, but basically in the first phase of the project we simply looked at a particular gamma ray that's produced when that neutron is captured by the deuterium in the detector. That gamma ray is distinctive. We later put several tons of ordinary table salt in the heavy water, and that increased the efficiency for detecting that neutron by a significant amount, and also created a situation where we could, by looking at the distribution of the event on our photos sensors, we could tell the difference between this case where there were many gamma rays being emitted, and therefore it was quite uniform or isotropic, compared to that very specific Cherenkov ring for the case where we're dealing with just electron neutrinos. And then finally, we put 400 meters of ultra-low radioactivity proportional counters that had helium-3 in them and detected neutrons directly. And that, I'll show you a picture later, was the third phase of the experiment with a separate measurement entirely of those neutrons. So what did this detector look like? Well, first of all, it was about the size of a 10-story building. It was 2 kilometers underground in a very active nickel mine, one of Inco's most productive mines, and it continues to be to this day owned by the Vale company. We had that 1,000 tons of heavy water that was about $300 million worth, loaned to us for $1 for 10 years. That's pretty good leverage in any market. And Canadian government agency that loaned it to us was really one of our tremendous benefactors, along with Inco, in providing us with this wonderful underground location. It was housed in a transparent sphere, which is 12 meters in diameter and about 5 centimeters thick. Tremendous construction project to build this, and also to build the remainder of the light sensor structure that looked in at the heavy water in the central region, because we were restricted to have everything in a mine cage, which was 3 meters by 3 meters by 4 meters. And so this detector had to be very modular and then reconstructed on site. So we looked in with these lights, this light sensor array, at the bursts of light that I just described to you. And we were very careful in terms of radioactivity. We surrounded everything other than the heavy water sphere with ultra-pure light water, and that was housed in a watertight and radon gas-tight liner. So we had graded radioactivity. You start with uranium and thorium, which is the main elements. Those are the main elements that create radioactive problems for us. They're about a part in a million in the rock, and in the middle it was less than about a part in 10 to the 15 of those elements. So 1 radioactive decay per day per ton of water. So the people that developed the radioactivity control systems, led by Dave Sinclair, did a tremendous job to make this project a success. The location is, as I say, 2 kilometers underground. It's down in a very active nickel mine. We traveled in this shaft and transported things to our site here, a very stable underground site, which we have used for many years. I guess I should have had the Eiffel Tower on there as the icon for this particular presentation. In the United States, I usually say that it's the entire state building that I should have as the icon. I have that on good authority because one of my sons at age 7, when we were at Princeton, went to New York City for a visit and came back and told us that he had seen the entire state building. So we proceeded from there with this construction project. You'll see that everyone in this picture is wearing lint-free clothing. The cleanliness aspect of this project was tremendous. Well, we had 1 million pieces. By the time we were finished, we had less mine dust on that entire structure than you could pile on your thumbnail, less than a gram overall. And that was essential for us to be able to do this experiment. We estimated over 70,000 showers and changes of clothing for people in order to maintain that cleanliness throughout the project. The water systems were a tremendous success. Everything was very clean. You can see the example of the floors here. When my mother visited, shortly after we got that in place, she said, "It looks pretty clean, dear." So I figured that was probably a pretty good affirmative statement with respect to how well we were doing. You can see here that we were posed with a substantial problem when Stephen Hawking visited, but Inco was very good and designed a special rail car to have him come underground, a very inspirational figure. This is the data that we obtained from the first phase of the experiment, in which we were capturing the neutrons in heavy water, producing a 6.25 million electron volt gamma ray. And this is a distribution. I'll show you in a moment how we calibrated that. This is a distribution that represented all neutrino types. This is what we expected from the charge current reaction that was only electron neutrinos. And we did a test of this, for which the results are shown in the next transparency. What we tested for is a hypothesis that neutrinos were not changing their type. And what we found, in fact, that what agreed with the data was something that had less than a 5 sigma possibility of, or less than 1 chance in 10 million, that in fact neutrinos were not changing their type from this data. And the most consistent result had a very good agreement between all of the neutrinos after the change of type had taken place and the total number calculated by the solar model, John Bacall and his group. And only 1/3 of the neutrinos were actually still electron neutrinos. 2/3 of them had changed to the other two types. When this result came out, John Bacall, who had worked for so many years on this, was quoted as saying that he felt like the DNA evidence for absolving him of many years of questioning had finally come in. And so he was, in fact, a very important part of this whole story of solar neutrinos. To show you how we were able to know that those shapes were in fact the way they would be, we had a source of 6.13 rather than 6.25 MeV gamma rays that we were able to move around within our detector with this rather remarkable manipulation system created by another one of our colleagues, and which enabled us to put a variety of different radioactive sources and other sources of gamma rays, in particular this one, at almost any location in the detector. And this is what we expected from the reaction that looked like that were created by electron neutrinos. And these are calibration data that we obtained with the other calibration sources. This is what we obtained with the neutron source as well. So we had the ability to know what shapes we would expect, and we could do fitting to see what it implied in terms of the physics. We also did a tremendous amount of work to be sure that that question of whether or not the numbers of gamma rays were great enough to have produced free neutrons simply from radioactivity, that they were low enough. Throughout the experiment, we set a goal of how much radioactivity we would have from radon gas in the water, from radium, and from, which is a daughter of thorium, and another radium daughter of uranium. And you can see that essentially, starting around the beginning of the project, and except for a few periods where we didn't use the data, we had met our goals throughout the project. This is making measurements with external techniques on the water system that we were using to purify the water. And we were also able to look at the data inside the detector itself, and we had several techniques for distinguishing between, well, a technique in terms of the isotropy of the events for distinguishing between uranium and thorium, and we could set limits on that basis as well. We were able to ensure that the numbers of events that arose from gamma rays breaking apart deuterium were more than a factor of 3 smaller than the actual signal, and we knew what that number was to better than 30%, giving us an overall 10% uncertainty in the initial phases and better later. This is the actual data that we obtained that I showed you earlier, and this is after we put salt in. You can see that what happened was that the charge current result essentially stayed the same, and the result from the neutrons capturing in the salt went up substantially. And what's interesting in this slide is that this is what we predicted. This is what was simulated in 1987 by another one of my colleagues who's here today. And you can see that the relationship between these parts of the data, as you can see here and here, and what we predicted for the radiation background wall, which goes up strongly in these two plots as well in the same location, is essentially the same. In other words, that's what we said in 1987 would be possible if we could actually do it, and the data in the later years shows that it was actually done. Another way of showing the results is to plot the sensitivity of the reactions to muon and tau neutrinos combined and electron neutrinos on this axis. This is the plot associated with the all neutrino sensitivity. This is the plot associated with just electron neutrinos in that reaction. You can see where they cross is our result. You can also see that the results shown by the black line here from doing the same plot for the SuperKamiokande data, and then with less accuracy, our own data from the electron scattering reaction is in very good agreement with it. You can see the uncertainty in all neutrino types is shown in this, this number here, and you can see the comparison at about, well, nearly 5 with the predictions with 5.8 plus or minus 1.3 from Bakal and from Sylvain Turkshiez, another very substantial worker in that calculational area, that the agreement with solar models is really very good. And by the time we got to the salt phase, we had more than 7 standard deviations, clear indication that the electron neutrinos compared to all neutrino types is about 1/3. We then moved on to a phase in which we installed 400 meters worth of very low background neutron detectors. Great success by the neutron detector team led by Hamish Robertson. But as an indication of how you do go through some difficulties in these experiments and have to modify things mid-range, you can see what the submarine used to install them ended up looking like. This is what it looked like when we first designed it. I mean, if you were going to build a submarine, what color would you pick it? Of course, a yellow submarine, except that particular yellow paint was very radioactive, and we had to scrub it all off and have a very mundane submarine in order to do our work. So if you include the great work that had been done by other measurements, including Kamiokande and SuperKamiokande on solar neutrinos, what you see is that in 1989, well, here is the first result starting in 1968 of Ray Davis, where the threshold for using chlorine is at this point. And so everything in terms of the different reactions as a function of energy, everything above this threshold contributes to the results. In 1989, Kamiokande and SuperKamiokande started to provide results that were increasingly accurate for the higher energy neutrinos. In 1992, the 2 gallium experiments, SAGE and GALAX/GNO, were sensitive to the PP neutrinos, and in all cases, these were either exclusively or predominantly sensitive to electron neutrinos. And so we still had a puzzle. In 2001, we started presenting our results. in 2000, before we presented our results, this is the sort of thing that you would see for the results as a function of energy, different reactions in the sun contributing to the results, and the theory being shown up here as a 1. And you can see there were deficits in all of the cases. By the time we had finished the 3 phases of the project, we had shown for all 3 phases that the total number of neutrinos was in very good agreement with solar model theory, and that the electron neutrinos were actually, for boron 8, being observed at this sort of level, and it is this difference that we use for that preliminary result I mentioned with SuperKamiokande. So, as was mentioned, neutrino oscillations are a case where flavor change can occur in an oscillatory fashion. In quantum mechanics, that is usually represented as the so-called flavor states, which is the state that's created when a neutrino is produced either by an electron reaction or a muon reaction or a tau reaction, that they are a superposition of states of mass 1, 2, and 3. And you can see what is now thought to be an indication of what those components are. Then as the neutrino travels through space, the mass fractions change, and then when you make a measurement again to ask how much does this look like an electron neutrino, a muon neutrino, or a tau neutrino, or in other words, in quantum mechanics, what's the probability that you would observe one of those 3 types, the fractions have changed. And so what you find, in fact, is that for muon neutrinos, you have that changing over the distance of the Earth, and in the case of the sun, you also have a change. It turns out that if you combine all of those experiments that I was mentioning, and others that have come later to measure solar neutrinos, you find that there's another phenomenon that has occurred in the sun, a phenomenon that was put forward by Mikheyev and Smirnov, working with previous papers by Wolfenstein, in which it is stated to be possible that if there is a significant interaction between the electron neutrinos as they pass through the sun with the electrons, the dense sea of electrons in the sun, you could have a transition which would be such that, as it appears to be occurring, such that the electron neutrinos get put into a pure mass 2 state and stay in that state as they travel from the sun to the Earth, and then end up in your detector showing up roughly one-third electron neutrinos and 2/3 the other types. That's a representation of that mass 2 state. In addition to that, what we determine with these oscillation effects is the difference in mass between the neutrinos, and we also determine this parameter for the mixing, which we refer to as theta 1, 2. Besides that, we were able to determine, because of that electron interaction, that mass 2 is actually greater than mass 1. That's something that's referred to as the hierarchy, and for the case of mass 3, relative to the rest, it's still an open question that may be resolved, we hope, by some of these many experiments that Professor Kajita outlined for the future. I'm going to talk about a couple of other types of experiments that we're going to be pursuing for understanding neutrino properties and also dark matter particles in the future. We now know that neutrinos have too low a mass to be the particles that seem to make up the dark matter in our universe, 5 times as frequent in our galaxy as the particles that make us up. So we're looking for other particles similar to neutrinos but heavier, referred to as dark matter. We've been very fortunate that we've been able to expand the laboratory in the vicinity of the snow detector in Sudbury to create a new area which has new experimental opportunities. We're also in the process of converting the snow detector to a new detector referred to as Snow Plus. And so what you see now is experiments in the case of Snow Plus that will study something called neutrinoless double beta decay, as well as further studies of solar neutrinos and neutrinos from the Earth. There are a number of experiments that are studying dark matter, and one that is studying supernova, as will the SNO Plus experiment. The list of physics that one is attempting to do with such experiments. In the case of neutrinoless double beta decay, we are converting the SNO experiment to a SNO Plus, a so-called experiment, putting an organic liquid that gives us 100 times as much light output, having returned the heavy water. And by dissolving in that tellurium compound, we can use tellurium as a potential for a potential measurement of a rare radioactivity, a half-life not quite as long as proton decay, but greater than 10 to the 25th years or so. So you've got to have a lot more than 10 to the 25 nuclei in order to make a measurement of that. But we think with 2 tons we'll have a good sensitivity. If this rare process called neutrinoless double beta decay occurs, it means that neutrinos are their own antiparticles. And if so, then it's also sensitive to the absolute mass, which we would like to be able to combine with the differences we've measured to give the masses of all the active neutrino types known. We have the halo detector, which reuses the SNO helium-3 detectors along with lead as a measurement of supernova. Recycling is a very big topic these days, and we're doing it as much as we possibly can in these experiments. There are also new experiments in which we're attempting to observe these dark matter particles, which are similar in their properties of penetration and difficulty of detection to neutrinos, but which are significantly more massive. And there are a number of experiments listed here which are taking place in SNO Lab. Now, I've emphasized SNO Lab because that's where we are working, but there actually are many laboratories around the world that are doing similar experiments to this. And we're very optimistic that with the progress that has been made in recent years and the excitement that has been generated in this field, that we will have a much more complete understanding of our universe. For example, there are theories that suggest that, in fact, neutrinos play a strong role in the conversion of antimatter to matter shortly after the Big Bang. We have a very matter-dominated universe, but it used to be roughly half and half after these were created from pure energy in the Big Bang. And so that decay process may be something that arises from neutrino processes, and some combination of what's being measured with the accelerator experiments and possibility of understanding whether they are their own antiparticles will be significant in attempting to understand those theories at some of the highest energies that we can imagine. These are our sponsors, and to whom we are very grateful. It emphasizes again that although this experiment took place in Canada, it was a truly international experiment from the very beginning, as you saw with Herb Chen being one of the founders and Dave Sinclair joining with the UK very soon thereafter. You see the list of institutions that participated in the project, and here you see the 262 authors. You can see that there are 262 authors, although you may not be able to read every name. Perhaps when this is put on the web, you can do that. And also 11 who have passed away since we started this project. I personally am tremendously grateful to this collaboration for all of the efforts that they've made over the years, and to all of the spouses of the people in this collaboration who are represented here today as well. So thank you to everyone.
We thank Professor McDonald for this wonderful talk, and now I would like to ask both laureates to come on stage, and I think we